All right, welcome back from dinner. Here we go. Pencils up. All right, so we're going to talk about, we talked about a lot about blade angle. Now we're going to talk about pitch, proper pitch, P-I-T-C, pitch, and what pitch is. So pitch, as I said, and I'll write this, pitch is often used as a synonym for blade angle, meaning the same thing, but that's incorrect. I'll write that. So pitch. Pitch is often used as a synonym for blade angle. But that is incorrect. That is incorrect. Well, I guess I'll write it. It's so one funny thing about, doing all of this in practically one night. It's like, well, I just said this, but normally it would have been, well, I said this like 3 days ago. No, so blade angle. Blade angle is the angle between, the face or chord, the chord of a blade station, and the plane of rotation. And the plane of rotation. All right, well, pitch, we'll make this 2. Blade pitch. Blade is the distance. The aircraft will move forward. Distant is the distance the aircraft will move forward. With 1 revolution of the prop. And this works better for those of you in second semester. Think of, everybody's at 309. So think of pitch in inches, like the pitch of a bolt or screw, like pitch of a bolt. How many threads per inch there were. So here, pitch. Well, I just wrote that. I'll have to write it again. Crazy. Pitch is based on, try not to be too redundant, but I guess what pitch is based on how far the aircraft will move in 1 revolution based on the blade angle at the 75% station. And let me see this one. No, I'm not going to do that. That's just redundant. Okay. So everybody follow that one. So if I talk about the pitch, truly, if I want to talk about the pitch of a blade, I should be talking about it in inches. So I shouldn't really say the pitch is, well, it's 20 degrees. No, I should be saying that I got something different to say. So it would be in inches. So A, B, C, we'll make this C. Geometric pitch. Geometric pitch. We're going to talk about geometric pitch and effective pitch. So geometric pitch, that is really what I just talked about up here. So everything I just talked about with the pitch is based on how far the aircraft moved in one revolution based on the blade angle at 75% station. Well, really geometric pitch, I'm going to redefine that. Geometric pitch it's the theoretical distance a prop would move forward, in one revolution, in one rev. I'll put one rev. Wow, this is it's a little redundant and over wordy, but I'll write it anyway since I started revolution. If it were, this is the textbook definition, if it were moving along a helix, having an angle equal to the blade. Along helix, having an angle equal to the blade. One more note here, and then I'll go to a slide. It is linear. And measured in inches. Just give you kind of an example, moving way ahead of where we are. And each manufacturer does things a little bit different. But like, for example, this is how Macaulay would do it. So if I wanted a Macaulay type propeller, and you don't even have to write this if you don't, I'll write it later. Macaulay part number is like a 1B 90 CM 7144. So that's an actual one. So here's the model number. That's the model number. So it's a 1B90. This is the style of the hub, basically. So when I looked back at I don't even know what this one's for, probably like 172 or something. If I look back over at my type certificate data sheet, I still have it up. Yeah, I do. What do we have here? Sentience Macaulay. See, they got the 1 AM 100 MCM. Okay, so I'm kind of talking about the same thing, 1-800, but it's a partial part number, 1A 100 DCM. And here I have a 1B90 CM. And so it's really those props were actually in the type certificate data sheet missing some additional information. But it's how the prop is pitched, if you will. Well, it's exactly what it is. So you can have a 1B90 CM, and you can have it in all different kinds of flavors, but this particular, and it said like not over 69, not under 67. Well, this one happens to be, this is the length, I guess you will.
The diameter?
Diameter. Diameter, yes, diameter. Thank you. That's the word I wanted, diameter. And this right here is the pitch. So that is to say that it's 71 inches in diameter, but it's going to move forward 44 inches for every revolution. So that is my geometric pitch. And it's put right into they stamp it right on there. And so the way they figure that out is, and what that last statement was, it's based upon a helix. And that goes back to this slide here. We can pull up, just like a screw. Yes, the propeller is moving in a fluid medium that has give and take to it. But the pitch is based on the assumption that it is moving along a helix. This is a helix. I hate it when I do that. I just touch the pad and it goes the wrong way. Moving along a fixed helix that doesn't change, or if you like, it's moving through jello, and the jello doesn't give. So for every revolution, that's how far it moves forward. In the same way, a screw in a nut, there is no give, right? For every revolution for a screw, if it was 32 threads per inch, you'd figure out how many threads that it would, how far it would go per twist. So it's the same thing. Yeah, we already talked about that. So that's what a geometric pitch is right there. I'm going to go over this. Don't lose your head over this. I'm going to use more math words. This, I believe, is one of the things that you have to do in lab. So now you have the opportunity when you get to lab, you can go back and you watch this and go, wait, what was that again? And if I'm not mistaken, there's a couple of different formulas for this one. I just happened to pick this one. Geometric pitch equals 2 times pi times the radius times the tangent of blade angle. And the example I pulled up here is we have a blade. So remember, you're always going to look at the 75% station. Where did I write that at? 75, right over here, 75% station. So that is what's going to stamped on the blade, the 75% station. So I have a 71-inch diameter blade. You should have your calculators out. Where did they actually measure to get this 4-inch? Let's see. First one to give me the answer in the chat wins a C's candy that I will eat for you and tell you how delicious it was.
53.25 inches.
Oops, hang on.
Or is it
Have to put it in the chat.
26.6?
Have to put it in the chat. I do not have 53.25. Did I do it wrong? Anybody else? Let me see.
53.25. So the whole length is 71, right?
Oh, wait a minute. Heath gets it right.
We need to divide it by 2.
Got to divide by 2.
The radius. Yep.
I done did it.
All right. Got to divide by 2 because we're talking about a blade.
26.62.
All right. So how did I do that? So for this one, it's 71 divided by 2 equals some number. I don't know. 71 divided by 2. I should know that. 35.5. So it's 35.5. Take 35.5 times 0.75 equals 26.626. So at the 26.6 station, blade angle is 44 inches. I'm sorry, the blade, we get the blade angle. I'm sorry, we get the blade angle. Now we're going to figure out what it does. So, so if we had a blade angle of 20 degrees, all right? So at 20 degrees at, we'll say this one is at station 30. So it's not this prop. I just pulled this one out of some notes. So at this prop that I made up right here, let's see. And then I just told you how to get that one. So geometric pitch is, so that'd be geometric pitch equals 2 pi times the radius. So what's my radius?
Diameter divided by 2.
Okay. Ooh, this particular example here, maybe I should go back and find my example. This actually is the radius at the 75% station.
Okay.
So, you know what I might do with this one? I think I'm just gonna,
It's 26.626. It's a radius at 75, right?
okay,
Yeah, but it's the radius
okay, I already
at
screwed
70.
up. I got half of you over here working on a 71 inch prop, and the other half of you over here at 30. I got to get everybody to move forward. Everybody's got to move forward and realize that this was one thing and this is something else. So go ahead, Daniel. What was your question?
So the station 30, it's means 75% from some propeller, right?
This is the 75% of some propeller.
Okay.
All right. So, and I got this right out of a book. I wonder if I should go back and double check their work on it. I just kind of took it for granted.
So it's mean we need to times multiply 2 pi times 30 times tangents of the blade angle of the 20.
Hang on a second. Let me get with you. Get my notes back where they were. Okay. So what is your question?
So we need to multiply 2 times pi times 30 and times tangents of the 20.
Yes. Okay. So everybody's with me now. We're going to talk about this new prop. There we go.
Wouldn't
New
it
prop.
be by 15 since it's the radius?
Okay. I'll go even more. Let me just fix these notes here just to make sure. Hang on. You know what? I'm going to skip it. Oh no, I'm sorry. It's even in my notes. It says correct this, and I didn't do that. So I just got to do that. So let me just fix that R over here. Let me start again because yes, there was an error in that book. And so here, so it's geometric pitch equals, and we'll just edit that last part out. Geometric pitch equals 2 pi times the radius, come on pen, at 75% station, at the station, times the tangent of the blade angle. All right, everybody follow? And so we're going to do this for a blade that has a 20 degrees at station 30. And I could have done the math backwards and made it more difficult and gave you a particular prop, made you divide by 2, and then come up with times 75, which would be 30. I don't know how to do it backwards real quick. So 30 divided by 0.75 equals, so was that an 80-inch prop? Did I do it right?
That's what I got.
80, okay, thank you. 80 divided by 2 equals 40 times 0.75 equals 30. Okay, so at station. So this is an 80-inch propeller that we're talking about here. So remember, 80 divided by 2 equals 40. There, my blade is 40 inches. 40 times 0.75 equals 30. This 30 is right here. So I went and I got a prop and I measured it and I found it was 80. And then I divided by 2, multiplied that by 0.75, and I found out I should be at the 30-inch station. So I measured out from the center of the hub out 30 inches. And then I used a protractor, a prop protractor, using it correctly. And I found out that blade angle right there is 20 degrees. Now I say to myself, as I want to know, well, how far will that go? What is my geometric pitch on that? Okay, so geometric pitch on this particular one is, let's see, 2 times, so it becomes 2 pi times radius at the is 30, because right here, radius at the 75 station, times tangent of the blade angle. Now, this is something that you can use your calculator for, or use a tangent thing. So let me see. So I go 20, and if you have your calculator, which I don't know if you do, 20 tangent, oops, sorry, tangent, this one is tangent 20 equals, and it's just a mathematical thing. So for this, I put in my blue calculator, I put tangent, and then it comes up with that. I just put 20 close parentheses and hit equal, and it's going to tell me that's 0.36397. So that's it, 0.36397. There we go. There. So geometric pitch is 2 times pi is 6.283 times 30 times 0.36397. And I do that. So the geometric pitch equals 68.61 inches. There we go. So that means that this particular prop should move 86.61 inches per every revolution.
68.61, right?
60.
You said 86.
Yeah, you said
Oh, just go with what I wrote. 68.61.
Okay.
Unless you get something different. All right. And where might the note go? Hang on here. So if going back to there, that's how I can find that. So if I don't know what's stamped on the prop, that's how I can find that. Or I could just look at the prop and it should coincide with that, with the part number at the end.
Excuse me, Kevin. It's a distance between how much the plane will be moved in the move forward, right? Or it's distance how the tip will move along the helix.
This is how, well, the tip and the hub move at the same speed forward. This is how far the plane will move forward in one revolution of the propeller.
Okay.
So when it's assuming, and that's, we'll go back to this picture, assuming that, back up one, assuming that you don't have slippages or anything else, that the propeller is actually moving through metal, if you will, that's cut at the same pitch. That's how far it will go. And of course, this is just representing fine pitch versus coarse pitch, but that's not really a point that needs to be made. So there's my geometric pitch, and I'll put this right here. So
is this at a given RPM?
No, there's no RPM involved. Look at the formula. It's simply degrees. The only thing that I had to know was how many degrees of the prop. One thing.
Oh, okay. I see.
So I took one piece of information from the prop, and that was this, 20 degrees. Now, I had to know where to get the 20 degrees. That's here, because the prop is different all the way down. So I got to figure, well, should I measure at the tip or at the hub? No, I measured it at 75% station. So at the 75% station, it is exactly 20 degrees. Do the math based on that one station, and it tells me how far the aircraft is going to move forward in one revolution. That is my pitch. So if I want to use pitch properly, it's in inches, how far the aircraft moved forward.
But then if you did that equation at a different station number, you're going to get a different measurement in inches.
I'm going to get a wrong answer.
Yeah,
Because
it had to be in the
this is
70s,
always
right?
based on the 75% station, because that's how the propeller is built.
Oh, okay. Yeah.
So if you want to think about it this way, which I do, they start with the 75% station, and this one is 30 inches out, and say, this is our spot. This is what we start with. We have to make everything else on this propeller work with that 75% station. So honestly, I mean, if you think about it, probably if we did the math, it should come up with the geometric pitch should be the same all the way around, because they built the prop to move that far all the way around.
That makes more sense.
Oh, good. Okay, so I'm going to say it again. This is the distance. This is the distance the aircraft. August said, so move forward 68 inches in one revolution. Yes, that is correct. 68.61 to be exact. This is the distance the aircraft would move forward in one revolution of the prop. I should put right here, theoretical.
As if it were a screw.
As if it were a screw. This is the theoretical, theoretical. This is the theoretical distance. So what does that mean? It means it doesn't do that. It's just a theory. So if it's just a theory, what does it really do? Well, we call that the effective pitch.
Probably more like 58.
The effective pitch. There we go. Well, that didn't work like I wanted it to. All right, fast forward, escape. Control-Alt-Delete. There we go. So the difference is the effective pitch. So what we just talked about was the geometric pitch, a mathematically perfect world-based formula. The aircraft would have moved forward from the yellow all the way out to here, to the gray, and that would be my geometric pitch. I wish it were. What really happens is the effective pitch, and that's based on how efficient the propeller is, its design and everything else. Because just because you put a stick out there and put 20 degrees on it, doesn't mean it's going to go that far. You got to have the right airfoil shape. You need to have the profile set right, the right chord, everything, you know, it's how well they built it. And so this gets into, ties back in what we talked about back in Aero 310 with thrust horsepower. How efficient is the propeller? So you have brake horsepower, then you have thrust horsepower, and thrust horsepower was really just brake horsepower times the efficiency of the propeller. Well, now we're looking at propeller efficiency right here. If the effective pitch equaled the geometric pitch, the propeller would be 100% efficient, and they're not. So this one right here makes it about here. That's what, about a 75% efficient? I'm just making up stuff between here and here. You can see that. So, and what's left over is slip. So we have the geometric pitch, effective, and whatever's left over is called slip. So effective pitch, here we go. It's the actual distance. Oops, the actual. The actual distance the airplane moves forward. Moves forward during one revolution of the prop.
And Kevin?
Yep.
And this changed with wind too, right? If you have a tailwind, then you're gaining more speed, you know?
I tend to think not. Because, and the reason why I'm going to say no on that is because that doesn't change the efficiency of the propeller. The propeller is still doing the same work inside of the same air. It's just that that air is also moving at the same time. Kind of like if you're going down a river and you're going upriver, your ground speed going through the river on a boat is slower, but you turn around and go downstream and you pick up a bunch of speed. The propeller on the boat is doing the same work as it was before. It's just moving in the water that's going. So that's my take on it. So I don't believe that the propeller suddenly becomes more efficient because you have a tailwind at all. You're moving inside of wind that is moving.
I'm not saying more efficient, it's just change.
Well, that's
Now
actually,
you're moving like not 60A, you're moving more than 60A. It's just
right, but that's because of the wind is moving you. So when we talk
Yeah.
about geometric pitch versus effective pitch, it doesn't change between a headwind and a tailwind.
Okay. Yeah, because you're talking mechanically. This is
Mhm.
what it is mechanically, right? This is what is producing.
Yes, I think we're talking the same thing. Let's see, point one. Small blade angle, equals less distance per revolution. And if we have a large blade angle, we would have more distance per revolution. And we'll throw this one out. Effective pitch can range from 0% to 85%. All right, so a couple of things to think about. When would a propeller be 0% effective pitch?
When it's not turning.
Off.
Nope.
When it's feathered.
It's totally flat or feathered.
No, I'm thinking of something different. If I have my engine running and I have it at 2,500 RPM and I'm on the ground and my brakes are locked, what is my effective pitch?
0.
There you go.
Because they'd move.
Because my geometric pitch has not changed. It's designed into the propeller. But my effective pitch is 0 because I ain't going nowhere. And then
That's a trick
85% would be in that perfect world where I'm straight and level at the exact right speed moving forward versus the exact correct speed of the prop going around at the RPM that they designed. Now think about this. We can add this all into there because now we know about stuff like this. And hopefully I don't lose my thought here. Okay, so we know that let's just say the designer of an aircraft and a propeller, and he knows all of this. He says, okay, well, I'm going to build a fixed pitch propeller and engine combination. So he builds this engine, and well, let's just take the example in our hangar up above us is that the Very Easy. So there's that Very Easy that hangs up there, and it's got an O200 in it. Well, I have an O200 in my plane. So we both have O200s. And so, well, my O200 has a prop and it fits on my plane. So therefore it would fit on that one, except for the fact that that one goes backwards, but just disregard that one. Let me just change this a little bit. So anyway, let's say I'm going to design a plane, and it'll be that Very Easy up there. We'll just go with that. And so I know that I want my propeller to be very efficient because I'm going to cruise my aircraft normally at about 65% power, right? And so I do some math and I come up and I say, okay, 65% power for this aircraft at 5,000 feet where I'm normally going to be working or flying around, because that's where I want to be, is 2,500 RPMs. We'll just throw out some numbers here. So I design a propeller that works great at 2,500 RPM, and it works well with the speed of the aircraft. And so I have to figure out how fast the aircraft is going to be at that one. And I figured out and say, okay, it's going to go at 150 miles per hour. So I match it all up and I get the right pitch and I make it and everything works good. So I get as close to that 100% efficiency as I can. All right. So you guys, I hopefully can see that. So that's where you want it designed. The right RPM going around and the right speed going forward, so that we have that triangle that makes perfect sense and hits so all along the blade, the triangle I showed you with the hypotenuse and that thing, every station on that blade is getting angle of attack is 3 degrees. You're like, I nailed it, right? And you take it out and you fly it at 5,000 feet and you're like, dude, it's like 86% efficient. I beat the thing Kevin wrote. Awesome. But then you decide you're going to go down to LA. And so you can take your plane down to LA. Well, on the way to LA, you've got to go over the mountain and there's some sort of condor reserve. And so you got to go up, it's like 12,000 feet, right? Well, we know that the higher you go with a normally aspirated engine, your horsepower starts going down, right? So what do you do to increase your horsepower to keep it at 65% power? Anybody? This is where you can chime in.
Increase
More
throttle.
Okay, more RPM. So I increase my RPM. What happens to the efficiency of the propeller now?
Goes down.
It's got to go down because the triangle got all messed up. The one leg got really tall, and so you're still maybe going the same distance forward. Well, you were, but the prop moves revolutions more, so everything gets all messed up. So you can see why there's going to be this huge range of 0 to 85. So 0, got my feet on the brakes, I'm on the ground. Best case scenario is 85, and you're going to lose at least, what's that, 15% always to this effective pitch thing. So anyway, something to consider. Let me see. Okay, so something else was at the top of my head. When one of you guys, and I'm not sure which one it's going to be, I'm looking around. When one of you guys comes back to City College in 5 years, 10 years from now, and is applying to be the next professor, this is one of the questions that was asked of me. And it was something along the line of, because you have to answer technical questions and stuff in the interview process. It was, what happens to the angle of attack of a fixed pitch propeller as it goes from stationary to flight? And now all you guys know the answer to that, right?
It increases.
Well, it decreases.
Decreases.
Right? 'Cause I think the actual question was, does it change? And, being out there, a mechanic in the field, this is not something that you think about every day. Let me tell you that. But you just work on them. You fix them. You're looking for cracks. You're filing out problems. You don't think about effective pitch and geometric pitch. And it's rare that somebody comes in and wants you to talk about repitching and what you can get. It's kind of rare. I was lucky that I worked in a shop where we thought about it occasionally. But to answer the question, what I had to think about is, as a mechanic and think about it, I'm like, okay, wait a minute. I know that when I work on a plane with a fixed pitch prop, I'm supposed to check the static RPM. And the static RPM is usually about 23 to 2400 RPM. And I know that the red line on an airplane is somewhere around 25 to 2700. So or around 27. So why would the red line be way up here and then my static is way down here? Let me think that through. And I thought, wait a minute, that's right. When my feet are on the brakes, the RPM is low, but as I start rolling, the RPM starts coming up. And then when I get into level flight, the RPM almost redline. So you think that through and it's like, it makes sense. The angle of attack was really high back when my feet were on the brakes. And as I let the airplane speed up, what happened is that angle of attack got more and more and more efficient until it was right there at like 1 or 2 degrees. And the airfoil was able to efficiently move through the air and give me thrust and lift. So anyway, that's how I answered that question in my own mind. And I said something probably different and unintelligible, but they still got the job. So, hey, good for me, bad for you. So, But anyway, I guess I tell you that story to hope that this is the thought process that you guys can kind of follow with this stuff and see where it can kind of work for you and why you need to know stuff like this. Because, you know, it really sucks if you're out there working in the field and someone goes, man, I got a problem, dude. And like, yeah, what's up? Well, I don't know. Every time I do a static run up, it's only at 2,400, but then I start rolling, it goes to 2,700. There's some sort of disconnect between my wheels and the power in my engine, and I can't figure it out. You know, every time my wheels start rolling, I get more power. Is there like a turbo built into my wheel? Like,
You say
no.
relative wind?
Well, it's like, yeah, it's all relative wind, man. It's all ball bearings these days, right? You guys know that movie? Oh man, nobody knows the movie, but
Vamos.
it's all ball bearings. I'll have to show you that clip. It's an airplane thing. All right, so slip, I'll finish this off before we leave for the day. Slip is the difference between. Yeah, Kevin likes my stories because I can watch him over there. He's like this when I start telling a story. He's a little. And we have the same chair, don't we, Kevin? Mine's just blue.
Kind of.
Yours is probably better. The difference between, where am I? Difference between, oh, geometric pitch. And effective pitch. Pen's not going to E, E, F, F, E, C, T. And effective pitch. So if we did a math problem, it is geometric pitch minus effective pitch equals slip. If the prop is 100% efficient, which it's not, efficient, geometric pitch would equal effective pitch, effective EP, effective pitch. All right, we'll wait for Eric to get caught up. He's good. Janet, you gonna check in? You good?
So, I'm almost done. Just give me a second.
Good. Janet's good. I don't know. Can we, as a class, we have to vote on if we allow Steve to drag us?
I'm good.
We don't even know. Were you in the shower, buddy?
No, I've been writing this whole time. I just been having my camera off because I had to move downstairs. My brother's down there.
Okay.
He's
All right.
only boxers, so.
Well, holy crap. Did we cover a lot today? Did we really start here today?
I guess so.
I don't remember.
I know. I don't remember either. All right. So we learned all about the nomenclature. We know why it was painted black. So now you can go and leave today and tell everybody about why the tips are painted a different color so the black paint doesn't slide off. The face is not this. This is the back. The face is the other side. We know about the metal tipping. I didn't show you this one. This is called a Q-tip propeller. I wrote that up there, Q-tip. And you actually see that out in the field. And it's like winglets on a wing. And I think they're pretty cool. It's funny that sometimes people will think a prop strike happened and it hit the tips, and that's what from a prop strike. I don't know, maybe somebody had a prop strike and it turned out to work better and left it that way. So,
Oh,
Do they help with turbulence or something?
well, yeah, right there. Reduces wake tip vortices, just like winglets would work. They say it's quieter, and of course it's shorter. When you guys talk about winglets, you'll know all about it. But they're out there. I just threw it in. That's cool. We talked about our blade station theory, our element theory. We now know that blade stations are every inch from the center line going out. Oh, we talked about blade angle and how blade angle is not pitch. And now you know pitch actually is how far a blade goes forward in one revolution. So that is pitch. So if I said to you that a blade that is straight up and down is at low pitch, you would look at me and go, wait a minute, that's not pitch. Yeah, that's a blade angle. But now you're smart enough to know that that's okay because it's often used interchangeably, just incorrectly. So we say that low pitch, high pitch, when really we mean low blade angle and high blade angle, but we use it interchangeably. And that's just it. So here we go. That is true pitch. Low pitch, small blade angle, high pitch, large blade angle. So the more the blade angle increases, the further we're going to go per revolution. So this one would go to here in one revolution. This one makes it all the way over to here in one revolution, 3 times as far. Oops. I probably hurt you when I did this, and nobody still knows what the hell I was talking about. But this was to explain to you. Well, I shouldn't say that. That probably demeans you. I was more a slam against my explanation than anything. But this was to explain to you why it is pitched differently at different stations. It all has to do with how far the blade rotates per revolution. Did the same thing here, showed the angle of attack breaks on and angle of attack breaks off. Same thing here, breaks on, starting to roll, and proper focus. So is Steven, isn't it?
what?
You're being noisy.
Sorry.
All right. This is one I believe there's quite a few questions on your Q&As. Geometric pitch versus effective pitch. So remember, geometric pitch is what you wish you had. Effective pitch is what you get. Slip is what's left over. And I think that brings me to tomorrow's points, and it does. So I hope you all have a good night. I'm going to go out and play with Zeus.